I'm calling this lecture Exponential Equations. We've learned exponential functions, and on Wednesday we did all these graphs of exponential functions, as well as then applying these transformations to the graph, expanding our notion of what an exponential function is and understanding that we can still multiply by these constants out front. We can apply these shifting factors, these plus constants, whether in the exponent if we're shifting along the x-axis, or plus a constant outside of the function shifting along the y-axis. But now we want to get into some problem solving, some of the analytic techniques. And these come about when, let's see, so we won't get to applications until I think the end of next week, if not later. At the end of logarithms, we'll get into some of these applications of exponential equations and exponential functions where we'll do exponential growth modeling. Hopefully, a lot of you guys have heard about COVID and the exponential growth of that. So, modeling pandemics, modeling the spread of a disease, modeling the growth of a bacteria in a culture, even modeling the population of the human race over a given period of time is all exponential modeling. And we can ask ourselves certain questions like, if COVID, let's say if COVID were to just run rampant and we didn't have any lockdown restrictions or anything like that, and it was just purely exponential growth, at least for its initial stages, we could ask, say, when will 2 million people be infected? Something like that. So we would have an exponential function to model this, but then we're asking an equation. We're asking when this function will hit a certain value. And then we have to solve this. So let's develop some of these techniques of how we can solve values for exponential functions. When will exponential functions hit certain values? One of the things you should have saw on Wednesday with all these graphs is that exponential functions are one-to-one. They pass the vertical line test. They're just these nice kind of concave up curves. Of course, they get really steep really fast, and then up to flipping and twisting and shifting. They're one-to-one. We can draw these horizontal lines, and the horizontal lines will only cross once. This tells us that they are invertible. So our inverses of exponentials are going to be logarithms, which will start on Monday. But the other thing that one-to-one functions give us is they give us a way of solving for variables. So let me explain that a little bit better. Let's just start off with a basic example. Let's say we have 2 to the x is equal to 8. This is an equation now. We have some exponential function, and I want to know when does this exponential function equal 8. And so our problem-solving technique at the moment is going to be to try to find a common base. It's not always going to apply because sometimes we can't do this step. And in that case, we'll need logarithms. But for these introductory ones, our first problem-solving method is if I can make the bases the same, then we can actually solve the problem. And so what we're going to do is, well, we see this base is 2. We can't really change it easily because 2 is a prime number. So we're just going to keep that base as it is. And nicely enough, the other number, 8, is a power of 2. So we can write 8 as 2 cubed. When the bases are the same, this implies that the exponents have to be the same. And this is because of the one-to-one property. There's only one value, so 2 to the x is going to equal 2 cubed at only one point. And that point has to be wherever the exponents are equal. And so we simply get x equals 3. So our basic problem-solving method for this is going to be find the common base, and sometimes there's a bit of work involved in manipulating these to have the same base. Second step is going to just be set the exponents equal. And then our third step is going to be to solve. So all of the problem solving techniques that we have for rational functions, for polynomials, are essentially going to be in this step, because these first two steps are really helping us. They're just like additional steps we have to do before the problem to then reduce it to a situation that we've already worked with, situations that we already know how to solve. And so let's do some more examples and just get progressively harder, but most of these I think should be pretty quick. So next example, let's say we have 2 to the x is equal to 1/16. Again, 2 to the x is a very nice exponential function. We like base 2. It's, the smallest base that's an integer base that will have increasing growth. It's an integer as well, not some fractional base, which are a little wonky to deal with. And so let's try to write things in base 2, but we've got this 1/16 on the right. And at least 16 you should recognize as a power of 2. So start trying to just get these in your brain of powers of 2. 2 cubed is 8. 2 to the 4th is 16. Other things, maybe the first 4 powers of 2 are good, if not first 5 powers of 2. The first 3 powers of 3 are good. First 2 powers of 5. Of course, any number squared, hopefully you guys should know. So 16 we recognize as 2 to the 4th. And now we see we've got 1 divided by 2 to the 4th. And so we can rewrite this constant of 1/16 as 2 to the negative 4. So since it's a fraction in the denominator, this simply means we have a negative exponent, 2 to the minus 4. And now that the bases are the same, we set the exponents equal. And there's no more algebra to solve there since our exponents were basic. Okay, so let's get a little bit harder, or a little bit different, I guess we could say. I'm not sure if it's much harder, but 25 to the x equals 1/5. Still got these fractions that we've got to deal with. But now, with this exponential function where the variable is, we've got a base of 25, which is a little weird. We can keep everything as base 25 if you want, but we would have to write this 1/5 as a base of 25 as some fractional exponent. And so it's actually easier if you recognize our common squares, common cubes, to manipulate those down to their prime base, essentially. So 25 is 5 squared. And I'm going to start that off by rewriting this base on the left. And actually, you know what? Let's go ahead and manipulate the one on the right too. So this is going to be 5 to the minus 1. Just because we don't like dealing with fractions, it's better to write everything as exponents as our goal. So 25 is 5 squared to the x. So 5 squared I put in parentheses, and you just got to be careful with all of your exponential operations. We've got 5 squared to the x. It means I multiply the 2 in the x. So 5 to the 2x is equal 5 to the minus 1. That's our first step. Second step, now we can set the exponents equal since the bases are the same. And now we got a little bit of solving to do. So x is just going to be negative 1/2. Okay, so let's throw a little bit more into these guys now, because we often have exponents that are not as nice as just powers of x or just x. So let's say something like 3 to the x plus 4 is equal to 27 to the x minus 2. So now we've got these linear factors inside the exponent, so it's upstairs. But the problem solving remains the same. We want to look at the bases first. We've got a 3 and a 27. So we want to manipulate those. Our best base to choose is going to be a base 3. So we can, 3 cubed is 27. So we can write 27 as 3 cubed. I'm going to put that in parentheses and then have my x minus 2 still raise that, right? That 3 squared or 3 cubed is just the 27. And now we have to remember that because we're multiplying, you have to distribute this 3 amongst the entire exponent here. So it's going to be 3 to the x plus 4 is equal to 3 to the 3 times the quantity x minus 2. This is going to be the most common mistake with these types of things. We'll see this a lot. So always be on the lookout for this error, and that a lot of students will multiply the 3 in x and forget to multiply the 3 in the 2. So you'll end up with something like 3 to the 3x minus 2, which is wrong because if we see down here, we'll get 3 to the 3x minus 6 once we distribute. Bases are the same. We'll set the exponents equal now. And we just got a linear equation, so we'll solve. I'll add 6 to the left, subtract the x from the right, and we get x equals 5. And then let's do one more example. We'll kind of throw everything in there that we've been working on. We'll make this one a quadratic. So let's say 2 to the x squared is equal to 1/8 to the x minus 6. So a bit more complicated now. Not only are the bases a little weird, we got a fraction, but I also have x squared in the exponent. But again, mind all the steps. Let's just do one step at a time. Step 1 is get the bases the same. We got a base 2 and a base 8, or a base 1/8. So base 2 will probably work the best because we can at least write 8 as a power of 2. It is in the denominator, so if we were to do this in steps, we've got 2 cubed in the denominator. Exponent stays the same. And then let's manipulate this 1 over 2 cubed to write it as 2 to the negative 3. That's all inside that parentheses. So we haven't messed with anything outside the parentheses, haven't messed with that exponent yet. And now we do got to remember to distribute the negative 3. So it'll be 2 to the x squared is equal to 2 to the minus 3 times x minus 6. And distributing 2 to the minus 3x plus 18 is going to be that exponent there. Bases are now the same, and when we set our exponents equal, we basically reduce the problem down to a standard quadratic equation. So let's go ahead and put everything on the left side. X squared plus 3x minus 18 equals 0. And this guy will factor as x plus 6, x minus 3. And so our two solutions, x equals negative 6 and x equals 3. So real quick, let's just practice checking these. One thing that's going to happen in logs is that you're going to want to get in the habit of checking your solutions, especially if you have these quadratics. With exponentials, so what was our domain for exponential functions? It was all real numbers. So we're never going to have problems if I plug these numbers back into the exponential equation, it's never going to cause any weird mathematical problems. But with logs, it will. So let's just get in the habit of maybe checking some of these answers as well. Like if you forget to do these minus sign distributions or these exponential distributions correctly, You can catch them by going back and just checking your answers in the original solution, in the original equation. So let's go ahead and write this out. Let's check x equals 6. It'll be 2 to the, negative 6. And that negative 6 is squared, is equal to 1/8 to the negative 6 minus 6. So this gives me 2 to the 6 squared is 36. And 1/8, this will be 1/8 to the negative 12. How do we know if those are the same? You don't want to compute out 2 to the 36. It's going to be an enormous number. But we can manipulate the right side. So 1/8 we showed was 2 to the minus 3. Now raised to the minus 12. And when we multiply minus 3 and minus 12, we'll get 2 to the 36 equals 2 to the 36. So that one's good. Likewise, our other answer was 3. That'll say 2 to the 3 squared equals 1/8 3 minus 6. And so we get 2 to the 9th is equal to, so again, let's write 1/8 as 2 to the minus 3 to the minus 3, and minus 3 times minus 3 gives me that positive 9. So both those answers check out, meaning we did all the math right, and those are the only two solutions. Any questions on those guys? About the only other thing we can kind of throw at you now are some of the either harder techniques where we've got something like an x to the 4th and an x squared, and you got to recognize it as maybe one of these u sub type quadratics, or sometimes this base and this base could be offset by a little bit. Like this is 1/8. This could have been like 4 to the x squared. In which case that would throw in another wrench, because 4 squared is 16. It's not 8 is not a power of 4. But you could then reduce both of those down to a base 2, and sometimes you get a little more complicated answers out of that, sometimes some fractional answers.